Okay, we'll start now the second session of today, last session, for 3. So we'll have 3 contributing talks, and the first one will be by Tomoyuki Yamakami, and the title is How Does Adiabatic Quantum Computation Fit into Quantum Automata Theory?
Thank you. And also welcome back from the coffee break. Well, so as you see, the main topic of my talk is the quantum computation. Okay, so just to give you a rough outline of my talk, and well, this is all about so-called adiabatic quantum computation. It's a type of the quantum computation. And I'm going to bring that subject into the framework of quantum finite automata. So that's the main purpose of this talk. Well, the adiabatic quantum computation has been proposed and studied for some certain period of time, but the people never really discussed the subject from the point of automata theory or language theory. So that's I try to fill the gap. So I'm going to explore some properties, fundamental properties, structural properties of the decision problems. So we are mainly talking about the decision problems or languages, right? Is that we try to solve those problems using adiabatic quantum computation that can be described in this, from the point of the automata. Okay. So let's start. So first, just to give you, some, overview of the current status of the quantum computers. The main goal of the study of the quantum computation is to build the quantum computers. Well, very lucky enough, we have some several existing computers. Those computers are actually sold so that you can actually purchase it if you have money. The first kind is solved by the D-Wave systems in Canada, and very recently, IBM also started selling quantum computers, so you can actually purchase it. And other companies like Google's and the Microsoft and the Japanese communication company NTT, those companies are they have been studying try to develop the quantum computers for some certain years. Probably within a few years, they are going to start selling quantum computers of their own. Well, all the computers, quantum computers, actually, some company they actually keep all the things in secret, so that we don't know exactly what kind of the system they are actually developing. But it seems to be they are going to use very different kind of systems. The adiabatic computation is the part of the so-called quantum annealing, and quantum annealing was actually used by D-Wave systems. Their system is actually running the quantum annealing, kind of the technology. So before going into the details, I just give you a very rough idea about the basics of the quantum information theory and the quantum computation theory. Just a very rough, I have only a few slides to explain everything. So, okay. So the basis of the quantum information theory is the qubit or quantum bit qubit. So that is very different from the standard bit. And well, we call it the classical bit because we are actually dealing with quantum bits. So, okay. So the quantum bit is the kind of combination of hit 0 and hit 1. Well, we use this strange notation to represent some classical bit 1 and classical bit 0. And then we have a combination of them. One of the representation of the quantum bit is that if you just think about it, a tiny particle like an electron or a photon or whatever. So they're actually spinning around the x. So you can actually determine the spin head, right? The spin head is actually looking up. That's corresponding to the classical bit 1. And if the spin head is looking down, then that's corresponding to the classical bit 0. But you can possibly take any direction. The spin head can possibly take infinitely many possible positions, right? So that's the power of the one qubit. And now we can actually put the many qubits at once, and then we operate those qubits. Now another representation is something like this one here. So you can think about the nucleus here, and then the electron is orbiting around this nucleus, right? But the funny thing is that they just stay in the particular kind of orbit. They're not stay walking around at random. So suppose the electron is staying or orbiting in this particular orbit. So we consider classical bit 0. If the electron staying in this particular orbit, so we consider this is 1. So one of the funniest things is that one single electron appeared in 2 different orbits simultaneously. So that's the combination, or we call it the superposition, not the 2 different kind of state. So if you have trouble understanding existing the different places at once or at the same time, maybe you can think about it in a wave, because the tiny particle is considered to be the particle, but also it's actually behaving like a wave. So supposedly you have the blue line wave, and you have another the green one, right? So you can always combine the 2 different waves, right? So that's a combination of the 2 different states, right? So that is much easier to understand. So the superposition is the linear combination, or mathematically speaking, the superposition of the one qubit is the superposition of the linear combination of the 0 and 1. And the alpha and the beta could be complex numbers. Okay. So when you actually, the computation of the quantum computation in general, they actually rotate or turn this big the particle. So that's represented. So when the computation finishes, you have to actually observe or measure the quantum state. But then when you actually look at the quantum state, then that collapses down to the classical state, either 0, 0, or 1, nothing else. But you can get either 0 or 1, but with some probability. That depends on how close this the ax is to the state 1 or state 0. Okay. And another interesting phenomenon associated with the quantum computation is so-called entanglement. So this is not observed in the classical world. Think about it, the state like this one here. So suppose that we have 2 qubits, right? And the 2 qubits, the first qubit is in state 0. Then at the same time, the second state, the second particle is in state 0. Or the first particle takes state 1, and the second one takes the same state 1. And both conditions happens with exactly the same probability, 50% chance, right? But now we have the 2 particles, so that we can actually separate those 2 particles, right? But still, they just maintain the same condition. So if you observe one particle and discovers 1, the second one is automatically turned into 1 without any communication. So that's the very fascinating phenomenon. But anyway, so that's it about the basics of the quantum computation. Okay. So now we just go back to the business, right? So so this is the same notation. So think about this one, those notation as just a vector in the Hilbert space. Okay. So 2 vectors, they are called the epsilon close that means the L2 norm of the difference between the two vectors is bounded by epsilon. Okay, and the spectral norm of this square matrix is just the largest size. And the commutator of the square matrices is actually defined in this way. Right? Now, well, we start with lots of definition. Spectral, the ground energy is the lowest eigenvalue of the square matrix. Okay, and the eigenvalue associated with this lowest eigenvalue is called the ground state of this matrix. Okay, the spectral gap is the difference between the lowest eigenvalue, that means the ground energy, and the second lowest eigenvalue. So the gap between the lowest one and the second lowest eigenvalues. So that is called the spectral gap. Okay, just to keep in mind those terminologies. Okay, now I just quickly explain about the quantifying automata because that is the one of the main thing here. So this is the brief history of the quantifying automata. Well, around the end of 1990s, the Moore crash field and the convex ladders, they proposed the idea of definition of quantifying automata. Particularly, well, they actually introduced the slightly different models. Okay, so when I say that one-way quantifying automata or just one QFA, the tape head always moves from left to right without stopping. But if I say it in two-way, so head moves either to the right, to the left, and also then I allow the head to stay still. So three possibilities. Sometimes people allow the head to stay still when they talk about the one-way quantifying automata. But in quantifying theory, people they call it the 1.5 automata. Anyway, so those are the very kind of an early stage definition, and later on, people actually extended the definition. One of the most general definition is the one QFA, like that one, with a mixed quantum state and the quantum operations. They actually introduced the mixed state. Well, earlier, I discussed about it as a qubit. That is actually the pure state. So then you can think about it as a mixed state. And those are actually done by Bainis and the Freiburg and so on. The number of people they actually talk about this model. And sometimes they call it a general or generalized quantifying automata. Okay. Now I just give us an illustration of this two-way quantifying automata. Okay, so instead of introducing the mixed state and the quantum operations, I just can give you a different formulation using the garbage state. So we have quantum state control, the state control part, and also we have the indicators telling that where the head position, where the head is, right? And also we have another tape called the garbage tape. So we need to describe where the head is, right? And the program of this machinery is given by the transition function. We call it the quantum transition function. And input tape, including the end markers and the input output, those are classical and fixed, right? At the very beginning of the computation. So those are quantum state. And also the content of the garbage tape is also the quantum state. The garbage tape is used to, well, on during the computation, if you find some information not important or not necessary to keep, then you just throw that information into this garbage tape. And this is actually considered to be the surroundings and environment of the quantum system. Okay. Now I just modified the definition slightly to deal with the adiabatic quantum computation. So this is called the one-way quantum quasi automata families. or 1QQAF. Wow. And we have, so this is a series of the finite automata in this form. And particularly, Q is the set of inner states, and we have the quantum operation that is acting on the Hilbert space of the linear operators, or just simply the square matrices, right, on the configuration space. The configuration space is spanned by the all possible inner states. Yeah. Okay. So the quantum operation means that the well, we have a bunch of the so-called Krauss operators here that satisfies a particular condition, like this one. So this is called the completeness condition. Well, particularly when k is equal to 1, that means we only have one single Krauss operator to define this quantum operation. So that is actually this one. Now this sign is a dagger. That is the the transpose conjugate of the square matrix. H is the square matrix, the linear operator. Okay, so taking the linear operator, and then you apply this one here, and then you get the linear operator again, right? So this is the modification of the linear operator. So now we have an input, because then we are actually dealing with the quantum finite automata in some sense, right? So this is the abbreviation here. So when you apply a sub x1, that is actually coming from here, right? And then apply a sub x2, and so on. So I just simply describe it in this way. So the important thing is ordering is actually completely the opposite, because in this way, it is easier to understand the the ordering of the input. But when you apply the matrices, and we have to apply it in this way. So it's just a little bit confusing. But anyway, so we start with the linear operator, and then to apply this operator one by one, according to what input you are reading. Right. So first you read x1, next one is x2 and x3, and so on. Right. So we just simply modify the square matrix, and then finally we get something. So this is the way we actually use the quantum finite automata to modify the linear operator. Okay. The important thing is what we get in the end. All right. Now I have to quickly move on to the main part of the discussion here, an adiabatic evolution of the quantum system. Okay. So I'm just going to try to introduce the system called an AEQS. And well, I just try to pronounce it with something more familiar, like an EX. Okay. So EX is the system. Well, technically speaking, that's just the tuple described like this one. The first one is the actually size function, and that's actually described the system size. Okay. And we have a standard input, so this is the classical one, and we have two important Hamiltonians that are acting on the evolution space. Okay. The Hamiltonians are actually the Hermitian matrix, or just a self-adjoint linear operators. Okay. And we have the pair of sets, those S sub ACC representing the acceptance, the set of accepting the states, and S sub REJ referring to the set of the rejection, well, the rejecting states. Okay. Then also we use an accuracy bound. Okay. Now I'll just explain how the evolution, well, the adiabatic evolution takes place. Okay. Well, this is actually a little bit physics. Right? Suppose that we have a quantum state, depending on the time, right? And suppose this quantum state, right, at time t, it satisfies this the so-called Schrödinger equation. And this is this equation describe then how the quantum state evolves. So here we have to apply it in Hamiltonian. So that is also depending on time. Now, so our system evolves according to this Schrödinger equation. So we have two Hamiltonian. This is the initial Hamiltonian, and this is the final Hamiltonian, right, for our system, X. So we define the linear combination of the time-depending matrix in this way. So whenever you're applying the numbers between 0 and t, when you actually put the 0, then as you see, we will get the first initial Hamiltonian. If you put t, right, we will get the final Hamiltonian. So if you just gradually move the t from 0 to capital T, then the square matrix changing from the initial state, initial square to their final Hamiltonian. So something like this, right? The important thing is that we have to look into the ground state of this matrix, and also the ground state of this matrix, right? As you see, all the matrices slowly changes, not dramatically changes, right? So when you think about the ground state of this particular matrix, that is changing slowly as you change the Hamiltonians, right? Finally, you get the ground state here. So that's the basic idea of the adiabatic evolution. So I just to give you just a little bit picture here, right? So this is the same picture, same PMP. So we start with the initial Hamiltonian. Then we actually give some energy a little bit. So they actually find that so this representing the energy level, right? So if you give it some time, then they actually find the lowest energy level, right, for this particular Hamiltonian. Now we change the Hamiltonian slightly, so the shape change slightly, right? Now the new lowest level is here, so this one is moving to here. And we just keep repeating this process, and then finally we just reach into the final Hamiltonian, and then they automatically find the lowest point here, right? So we don't need to give much the computation physically, but they naturally find the lowest point. Right? It's more like you just put all the information into the test tube and shake it for a while. They automatically find the solution, kind of. Right? So that's the basic idea of the adiabatic computation. Okay. So now we just go back to the definition here, right? So this linear forms give the gradual transition from the initial Hamiltonian to the final Hamiltonian. Now we can naturally find the ground state, right? So, but the ground state may not be exactly the same as the original quantum state, right? So we say the evolution time, right? The minimum evolution time means that how much steps or how how many steps we really need. Because then if you take it in a bigger t, then you just slow down the process, right? If you take much bigger t, you slow down farther away, right? So if you take enough time, then everything is go smoothly, move from the first ground state to the last ground state, right? And that the final ground state must be very close to the target quantum state. If you can generate this state very easily, then there's no problem. But then sometimes, often this state is very hard to generate. That's why we need this, gradual process to approximate this final state. Right? Now, runtime or running time of this, X, the whole system, is the minimum evolution times the max time. So this is the spectral time. Yeah. Okay. So how big this T sub X is? So this is actually the law amount. Well, this is a very famous theorem called an Adiabatic theorem. And now you see that this is the factor here, and also here the spectral gap here, and also we have the epsilon here, right? So that's the closeness factor, right? So we try to make this one is big or small as possible. So that's our goal, because this is the spectral gap, generated from the H NE and H fin, right? So we carefully choose the first initial Hamiltonian to the final Hamiltonian. We can actually make this one small, right? So that means we have a large, well, not big T sub X. But if you have a very small gap here, then we will get the really big T sub X. Probably it's not practical to take that number. Okay, so I'm just running out of time, so I just quickly go over. Right? So acceptance and rejection are actually defined by how ground state is in this particular the Hilbert space, or this one. This is actually generated by the Q sub ACC. They are created by the accepting states, and this is created by the rejecting states. Okay, so the first lemma said that if you don't put any restriction on the machinery, then our system solves all decision problems. So that means for given decision problem, any decision problem, so we can always define the system that solves it, right? So that's a good story. But it's better to put some restrictions. So we will think about several restrictions. For example, system size, right? And the size of the spectral gap, just polynomial over 1, or constant over 1, or so on, right? And also we have to think about an energy level, right? Zero energy and probably 1 over polynomial energy and so on, right? And also we have to specify how to generate Hamiltonians, right? Now the system here, 1QQAF comes in here, right? So this is quantifying an automata. Okay, so a few more slides. All right, okay. The accuracy, okay, so this is the definition here. The AEQX, so X of F, is a class of language solved with the high accuracy using this system. And satisfying some restriction specified by this F. Right? Okay. So I'll just give one example here, the very quick one. So this is a very simple language, A to the 2 to the n. So that's a unary language, right? So we want to solve this question or recognize this language using this X. So we define something like this one. So we take the size of 3, and then we use an index, and Q0, Q1, Q2, and it looks like more like the quantifying automata, right? So we set Q1 to be the accepting state, and Q2 to be the rejecting state. And we define the bunch of so-called unitary matrices. And finally we define the initial Hamiltonian, the final Hamiltonian in this way. It's just 3 by 3 matrices. It's very simple, small one. Then what happens here, right? The final Hamiltonian is described by this way. So now you see that L of x and L of x bar, so that's a negation of it. So those are coming in. So either 0 or 1, right? So now we will get the result like this. The ground state of this final state, the final Hamiltonian is if x belongs to this particular set, then Q1. Otherwise we get the Q2. So So that means the ground energy level is 0. And we define the accepting state and the rejecting state to satisfy this one. So our system completely solved this question. Right? Okay. So else sub even, it belongs to this one. So 1 QQAF and constant size, constant gap, and 0 energy. Okay. So well, we have a bunch of questions, right? Because I just introduced the basic idea of how to implement the adiabatic quantum computation in the framework of quantum automata theory, right? So we just simply full-fledged theory. We really need it, right? So we need a lot more research, and also we have to really find out how to use adiabatic quantum computation, right? Using finite state automata. Okay, well, thank you very, very much for listening, and I'm really happy to take your questions. Probably I don't have much time.
I think the questions can be later in the
Okay.
during the trip or.
All right.
Okay, so.
Well, thank you very much.